Okay, in this section, what I'm going to do is show you how to do the proofs of our new system, language of monadic predicate logic. So we've gotten three new rules: existential introduction, universal introduction, and universal elimination. So I'm going to show you how to execute those rules and how to solve these sorts of problems. Here we have one premise, one conclusion from our first premise. This says there does not exist an X such that it's both F and G. From here, what we're going to have to do is we're going to have to think about the conclusion. This says for all x, x is f. If x is f, then x is not g. So what we need to do is to create a universal sentence for which we could use universal introduction. And so we would use universal introduction on something that looks like fa arrow, not ga, right? And so if we knew that we could universalize this sentence, we could create this sentence here, our conclusion. And so this is a conditional, and we should be familiar with conditionals. If we're going to make a conditional, what we need to do is assume that our antecedent is true, right? And so we're going to assume this antecedent, and what I'm going to do is write a note that this antecedent should be used for arrow introduction so that we can discharge the assumption, right? And then next, what we have to do is try to derive our consequent so that we can put that together with alpha is f. So to derive this, which is a negated sentence, we're going to have to use negation introduction. So if you're going to use negation introduction, what you should do is assume the opposite of what we want. What? Right? We want negation alpha is g, right? And so what we do is we assume the opposite of that, right? And this we'll do as negation introduction. That is, we'll discharge this assumption when we use this rule. Okay, so from there, hopefully it's a little bit more apparent that this is going to create a contradiction for us, which we're going to use in order to use negation introduction. So from here, we'll see that our premise says that nothing is f and g, and yet we've just assumed that alpha is f and it's g. So that means that alpha is f and it's g, that it's both f and g. So that is a rule of conjunction introduction, which we've learned from last time, right? And the dependency numbers are 2 and 3. So this doesn't yet create our contradiction, right? Because it's not the exact opposite, but it can be. And so here, since A is F and A is G, that means that something, right, is F and G. So here, if we know a particular object is F and that object is G, we can infer from that that some object, X, right, is F and G. So from 4, we know that some object is f and g, and so that's existential introduction. Here we can always replace the constants with a variable if we're going to use an existential quantifier. So from the particular to the general, and that general statement is an existential, is pretty straightforward. Okay, and so from 4, that is 2 and 3 for the dependency numbers on 5. So on line 6, what we have now is a contradiction, right? And so you sort of have to still be very careful at what the contradiction consists of, because they must be exact opposites. So here we get to write down the lambda, and that the contradiction is created from lines 1 and 5, and the rule that we need to cite is negation elimination. So because 1 is being used, we now add 1 to our dependency numbers. So with this lambda, we can use negation introduction, right? And what we want to do is use negation introduction on the third line, right? And so negation introduction is used on the third line along with the lambda on 6. And because this is a discharging rule, we discharge 3 at this point, and so it should be 1 and 2. And we said that since we've now gotten our consequent, we can form our conditional, right, which gives us what we were looking for. So here we form our conditional with arrow introduction, or conditional introduction, by putting 2, our antecedent, with 7, our consequent. And so here we must discharge 2, because 2 is an assumption, and it's being used with arrow introduction, which is a discharging rule. So now we only get 1 as the dependency number. So that's actually very important, because what we're going to try to do now is universalize this statement. If you notice that this statement, it's a particular statement about A, right? That A, if A is F, then A is not G. That's only talking about one particular object. And so what we're trying to infer is that all the objects, right, if it's F, then it's not G. And that may sound a little strange, because what we're doing is reasoning from a particular to a general statement. More importantly, we're inferring from a particular statement to a universalized sentence. And it's strange because normally we don't do that. Normally we don't, go to a restaurant and think that just because this restaurant is bad, then all restaurants of the same kind are bad. Okay, so this is from 8, universal introduction. Here we can make this kind of a move, but it's restricted. We can only make this kind of a move and use this rule, universal introduction, if our constant, right, here our constant is alpha, or A rather. A is being changed into the variable x. If A does not occur within the dependency numbers used on this line, then we can universalize it, or replace it with a variable. If it does occur, then we cannot. So here what we have to do is pause for a second and say, does alpha exist in line 1? It does not. And so we are safe to universalize on line 8 to line 9. Right? And so that's why it's very important to discharge the dependency numbers at the appropriate time. If we had either 2 or 3 within the dependency numbers here, we would not be able to universalize, because A would exist in 2 or 3. And so that's why we discharge when we do. So that's a very important point to consider. Okay, so let's move on to this problem down here. Here it says that not everything is F, and so that must entail that something is not F. Hopefully that's straightforward. So what we're going to do is list out our premises. Whoops. Not everything is F. Right. Okay, so we're trying to prove that something is not F. Here, because I'm sort of familiar with this proof, what we're going to have to do is do a reductio ad absurdum right from the beginning. And so remember, to use the strategy of reductio ad absurdum, you assume the opposite of what you want. What we want is there exists an x such that x is not F. and so the opposite is negated. So here we're going to assume it so that we can try to find a contradiction, which we will find a contradiction since we know that this argument is supposed to be valid. Okay, so from here we must also think of a way to create a contradiction. And again, you've got two negations, and it's very hard to work with the negations. And so what we're going to have to do now is try to think of a formula that would get us a contradiction. This says nothing is not f, right? And so if nothing is not f, then if one particular object is f, then it would contradict that. And so what I'm thinking is that if alpha is not f, eventually we will get a contradiction from this. And that's because if alpha A is not f, right, then we know that something is not f. Right. So if we assume 3, we can get to 4 with existential introduction. Oops. Okay, so there's a contradiction here between 2 and 4. Right? 2 says that nothing is not f. 4 says, well, something is f. Not f, I'm sorry. So that creates a contradiction. And so from 2 and 4, we get negation elimination. So that's 2 and 3. So here, on line 6, right, with our negation, we actually don't want to negate the second line, our first assumption. We want to negate the third line. And so this is important because we're trying to get rid of our assumptions one by one. So if we negate our third line, we get a double negation that looks like that. So this is line 3 and 5, negation introduction. Now you'll see here why I'll negate this and also why I've assumed this. So if I assume it's not the case that A is F, I can get the case, it is the case that A is F, given the contradiction. So, oops, 2 and 3, always do that. Okay, so line 7, right, I can get A is F from 6 double negation. Oh, no, that's not supposed to be there. Right, because this is a discharging rule. And you're supposed to discharge 3 at that point. And that's actually why I did that in the first place. Okay, so because 3 is supposed to be discharged at 6, right, 3 is not supposed to be there. Now, if you look at the assumption on 2, right, 2 is an assumption of a general statement. There's no constants in there. There's no lowercase letters a through w. So on line 7, there is a lowercase letter. So what we can do is actually universalize this sentence so that from A is F, we can make for all x, x is F. And we can do this, right, because this doesn't run into one of the restrictions that we had. Right? The restriction is that if A occurs in the dependency numbers, which occur on the line we're trying to universalize, right? We're trying to universalize this. Does A occur in its dependency numbers? We look back at 2, and it doesn't. And so we can universalize this safely. And so because we can universalize this, right, 7, universal introduction, it creates another contradiction between our premise and what we've just inferred, right? So on line 8, right, we've gotten that. And because of the other contradiction, right, on 1 and 8, negation, elimination, we can now use this this contradiction to negate our original assumption. So on line 10, we can say it's not the case that there exists an x and x is not f. So that's line 2 and 9, negation introduction. Okay, so discharging rule, which means that we must discharge the assumption that we used along with it, which is 2, and so this ends up to be just 1. Finally, on line 11, we can get rid of the double negation and create the formula there exists an x such that x is not f, which is our conclusion, right? And so that's from 10, double negation, and the dependency number is just 1. Okay, so that's how we can do these proofs. This sort of proofs are used, or rather they're executed without the use of existential elimination, which we haven't learned yet. And so I'll do more sample videos on the full set of predicate proofs, predicate rules, I mean. Okay, so hope that helps. I'll be back with more videos.